Hello developers, let's start developing. Today we're gonna take on the day 13 of the 2023 Advent of Code. We're somewhere on the lava island. It doesn't have any lava and we need to fix some problems. But first of all, we need to go through some kind of a, well, it's not a maze, but it's not that it's not a maze anyway. It's a matrix. More correctly, it's a series of matrices. And so far, I think that everybody knows how I dislike doing all those index calculations. Still, it is what it is. This is our demo input that we have, and it's worth noting that the good thing is that we have a series of matrices which are not connected, at least not in part 1. Anyway, our processing code should be able to actually take care of that somehow. Let's see. So, as always, first of all, I will get some basic types so that we can have a type that's called, what is this? Ash and rocks. Let's call it a floor tile. Floor. It can be a dot or a hash. That's what we need to do, and then our input will actually be a series of floor matrices. Yeah, it's this, and our input type is gonna be, we will need to replace this with this, a series of floor matrices, which means that we need to somehow get those. All the matrices are separated by an empty line. So we need to make sure that the first 7 lines step into one of the one floor matrix and the second 1, 2, 3, 4, 5, 6, 7 once more step into another. So far, that's all that we're gonna do. We're not getting into the details of the tasks. So we're gonna have to say, well, create a floor matrix. We will have a result that will be a empty array as floor matrix array, as a floor matrix array. And now we will generate one of these. The first line is actually full, so we can say let line is equal to lines dots. Yeah, we can use this thing. So we're using shift to actually take the data one by one. We're changing a bit, so this is kind of memory wasteful, but it's maybe a little cleaner to see. We don't need to take care of the index because we're always taking the first item of the array, but by taking it, we are removing it from the array. So the next time we take the first item of the array, we take the item that we actually want. So while line is not equal to the empty string, like this one will be, we will just need to map something. So we will split the line and get a row, and a row is an array of floor parameters, floor types. Yeah, that's it. We have some result and we're pushing on this. Not really. So we're gonna need to have a nested while loop, which is a thing of beauty. So while we actually have lines is bigger than 0, while we have lines, we're gonna need to loop through this. While we have lines, we're gonna say const floor matrix is a new floor matrix. So we take a single row and we can push that row inside the floor matrix itself, not on the row as an array, but like that. So we take the next line, and at the end we actually push the floor matrix inside the result. I have no idea whether this will have an issue at the end, but one way to find out. If we only get one matrix, then we need to add the last matrix manually. I think that we will get that, but one way to find out. It says that we have a string array somewhere because we're returning lines instead of returning the result. Well, we have something even worse. This thing never ends. Where do we have a basically infinite loop? We are on the second one. And actually, this is the correct thing. Yep, this will work because we need to take care of two things. This line, which is an empty string, and the line that's on the 16th position. So that will actually get us undefined. If we want to shift something out of an empty array, we will get undefined. And we are using the falsy nature of JavaScript to actually have two while conditions, two conditions in the while not having neither, but this still doesn't work. Did I say yes? So, okay, now we debug. I'll just put in a breakpoint here. Wait for the debugger to auto attach. And let's see what happens now. Well, we have lines, and the lines has a length of 14. 14. Oh, yeah, we already took out one. And line is truthy. And lines are 13. And our line is the next line. So we're going so on and so forth. Let's see what happens now. So let's see what we have in lines. In the lines, we have the 7 lines of the second matrix. In the result, we have nothing because we just pushed our first matrix. And we're looping once more. Oh. Oh. And now line is perennially empty. We're not skipping the second line. So here we have that our line is an empty line. So we will shift it once more. This might work, it might not. It will work in order to take the second array, but I have no idea whether it will actually break after that. So we're getting here, we have the lines, we're pushing the first thing. So now lines is 6 and line is actually the first line of the second matrix. So we are pushing that and lines should be empty. And we are returning the result and we are getting that we have 2 matrices. Let's test this out on the bigger input. This thing will, so our code so far just counts out the number of matrices. It doesn't, of the floor matrices. It doesn't do anything else. No need for breakpoints. Let's just run it, and it says we have a nice round number of 100 matrices, which sounds about right. So now on to the task itself. So each task is separate. Each matrix is a separate task, and it means that we need to find a line through the matrix. It can be horizontal or vertical. That actually makes the matrix into a mirrored matrix. And we are kind of guaranteed that each matrix will have one and only one of those lines. And then we need to get some value, so to say. If we have a matrix, if we have a column vertical line, then we just add it. And if we have a horizontal line, we add the line multiplied by 100. So actually the 405 number is comprised of 400 and of a 5, which means one had a column index of 5 and the other has a row index of 4. A weird way to encode data, but okay, that's the point of the task. So we have in our first matrix that we need to find out whether there is mirroring, where the mirroring line is. We're gonna have a mirroring line. So we need to actually have a line, generate all those lines, and then test them. Can this line be between 1 and 2? No, because these two are not mirrors of each other. Can it be between 2 and 3? No, these two are not mirrors of each other. Can it be between 3 and 4? These two are mirrors of each other. The 2 and the 5 is a mirror of each other. The 1 is not a mirror of the 6. And so on and so forth. And we will get that here we have this thing that is mirrored with this thing. So that counts for the first row. And we can continue on for the second row. So what I want to do is we will actually just map the input. For each floor matrix, get the mirror index or something like that. And we will have a method that will actually do that. So we are providing it with a single floor matrix, and it should return, let's say, -1. For starters, just to see if this thing works. If we are correct, we should get a -2 as a result. Not the correct one, but in the right direction, and we got 2 because we are not returning the correct data. This should be a sum function. And we just return mirror count. Now we should get -2. Yep, that kind of works. So now I will just we will need to do 2 things here. We will need to process row-wise, and then if that doesn't work, process column-wise. How do we process row-wise? So for each of that we're not concerning ourselves with x's and y's in this part, so I will just call this row index. Floor matrix dot length, and then we have a thing called a row, which is this. Now we need to check if this row has some mirroring points. And what would be a mirroring point? A mirroring point would be an index, and we're gonna have a number for that. We need the number of columns to the left of each vertical line. So the number of columns, so this thing here is actually 5. So this is vertical line number 5. Here we will have vertical, between 1 and 2 we have vertical line number 1. Actually, this is a trick because these are not the indexes. The indexes are 0 to 8. So between element 0 and element 1, we have the mirroring line 1. So we need to take the bigger index. And there could be up to, if we have 9 elements, we could have up to 8 for mindex. That will be mirror index from 0 and it from 1, because 0 is not possible. We need to do it up to the length of the, so we can have length equal row dot length. We can just use row dot length here. That's the possible mirroring points. Actually, I will do it another way. Not like this, but array, not fill. Yeah. Fill it with zeros and map it. The value is not important. We just need the index. But map this to index plus 1. So if I'm correct, this should give us for each array just index of all the columns. One, if it has 8 columns, it gives us 1, 2, 3, 4, 5, 6, 7, because we actually have 7 possible mirroring points. So I'm just saying that all of these 7 are candidates for that. The arrays are the matrices are kind of similar in the same width, so, and the same height, so it seems like this is correct. So we have 1, 2, 3, 4, 5, 6, 7. Do we? No, we're taking the horizontal ones right now. Sorry. We're handling the rows. So we have 1, 2, 3, 4, 5. What the heck are we doing? Then this is why I hate matrices, because we want to process row-wise. When we're processing row-wise, we are looking for the horizontal ones. Are we? How many horizontal points could there be? If we have 7 of this means that we can have up to 6 splits. So we're gonna do it like this. Yep, this is what we want. So at the beginning, we say that we have all these are the mirroring points that are possible. So we don't know anything about the array, so we say it could be 1, it could be 2, it could be up to 6. But now I will just loop through this, and for each row, no, but the horizontals, no, we need this. And row-wise and column-wise is tricky because we want to say whether we want to look for verticals. So now we will be looking for vertical lines. And let's see how many of those we got. Since we have 9 elements here, that means that we have 8 possible division points, mirroring points, so to say. Do we get 1 through 8? Yes, and before we start, all of them are possible. The world is the oyster. And now we're gonna loop row by row. So we are having that row, and for these values, actually we can just say, yeah, so these are actually the same range that we have in our mirroring points array. It will give us 1 and 2 and 3 and 4 and 5 and 6 and 8. So we have this row. Let's say we have this row. And let's do it here a bit. That has the indexes 0, 1, 2, 3, 4, 5, 6, 7, 8. So we're going to say if we have a line between 1 and 0, is this a possible mirroring point? We just need to compare those two. Is this a possible mirroring point for this row? So basically, if we have, let's have a stupid code like this. If these are equal, actually the other way around. If these are not equal, we can just throw out that mirroring point. No, but what I want to do here is to do, yeah, for mindex, but the mindex will not be that. We will actually loop this mirroring points array, and we will have the m point, which is the mirroring point, is mirroring points of mindex. So we are looping through the actual array, and this will give us point 1 or point 2. And then we can check if the mirroring point is valid. If that mirroring point is valid, what does that mean? It means that we can start from that mirroring point, move leftwards and rightwards. Let's say let left equals m point minus 1, let right equals m point. And if, yeah, while, yes, something like this. So while left is bigger or equal to 0, so we don't go off the grid, and right is less than the row length, which means we don't go off the grid in the other way. If the values are different, then this is not a mirroring point. And we can just remove it from the array. And now we have an opposite problem of the one that we had before when we changed the array that we iterated on. That time we were adding data to the array we were iterating on. Now we need to remove data. So in order not to skip any data, not to do any kind of issues, we will remove the current value because we proved that it's not valid. We will reduce the index so that we stay on we will actually the next value right now becomes at the current index. So we will go down one and then the for loop will go up one. So we break out of the while and we're done. And we can go to the next thing. Otherwise, we're gonna reduce left by 1 and we're gonna increase right by 1. So this will expand our search until we get to that. So let's try to actually debug this. Because I'm not really confident that this would work. It might, but it might not. So we have our first row. It's this. Our first mirroring point is mirroring point 1. Left is at index 0, right is at index 1. These are different, so we should just say this and then break it out. So right now the mirroring point starts at 2. And the index is actually -1 and it's going to become 0. Yeah, for loops are funny like that. So now we have our endpoint of 2. And we need to change our rows, so we're checking these two. Those are also not equal. We're removing because that's not a possible mirror point. So the next mirror point is 3. And if we take a look at the row, then we're gonna compare these two. They're equal. Then the next one are also equal, but the next ones are not equal. So 3 is not a viable mirroring point. Same thing, not a viable mirroring point. And now I think we get to 5. You can see that we're left with only 4 mirroring points. And 5 is actually the actual mirroring point because that's what the task says. And now I think that left becomes 0, right becomes 9, and we're out of options. We are moving on to the next mirroring point, which will be 6. Nope, doesn't work. 7 works for a while. It actually works. 8 doesn't work. We run all that row. So for the next row, we only have 2 possible mirroring points. So our mirroring point can either be on a 5 here or on a 7 here, because we run out of space. And looking from 7, yeah, it could be mirrored for that specific row. But what happens for the next row? For the next row, we actually take that one out as well. So we only have one option left. And that one option left will stay constant because it is an actual mirroring point. But what happens with the second array? Because the second array doesn't have a vertical mirroring point at all. The second array, let's process it for the first row, and right now our mirroring point is just possibility that 7 is a mirroring point, and then, yeah, 7 again. And now 7 is also gone. So we have absolutely no mirroring point horizontally. And this is more or less an empty for loop. It will just say you don't have mirroring points, going to the next row, you don't have mirroring point, going to the next row, and it will just loop through. So now we can just say mirroring points of 0, because we either have one or none mirroring points. And actually, let's do it this way. Because now we can just say console.log mirroring points. No, result. If I'm correct, we should get a 5 and an undefined. Yep. Because the first, we are only looking for vertical lines. The first one has a vertical line. It returned a result. The second doesn't have a vertical line and returned undefined. So I will call this V mirroring points. And this is actually a constant because we're not doing anything. But now I will just redo all of this column-wise, and working column-wise with matrices, because there's no such thing as a matrix. In JavaScript, there is a thing that is an array of arrays. So now we need to work, when we're working with rows, we're working with a single array. But with working with columns, we're working with one elements each of many different arrays. So we will need to do something else. But now we take the length of the matrix, because that is the possibility of all the mirroring points. They need to split a column, and instead of index we will have index, and instead of floor matrix length we will have floor matrix of 0 length, and the column, not the row, is we take the floor matrix, and for each element we map each row to its index element. So this will actually get us a column. And now for every horizontal mirroring point, we get that mirroring point. We have our left, we have our right, and since we transform the column, we can actually use the exact same code. Only we need mirroring points and not mirroring points. Let's just comment this out and see if we have any errors here. We don't, which means that we are using it properly. So I will actually define the v result. It's this or 0, and we will have the h result, which is this or 0 times 100, and a console log v result, her result. Exactly one of these should be 0, and then we just return their sum. One of these values will be 0. And I think that we can have an optimization as well, but let's just see it. Yeah, so we have 5 and 0 and 400. Let's try it for the bigger input. And maybe this thing works. We will have 100 pieces of data, and we have something that looks okay. I don't think any cases when we have two values or something like that. It's 41 milliseconds, but we had some console logs. Let's remove that and run it again. 4 milliseconds. However, I did notice one thing that we can optimize. We can just say, if this has a length that is 1, we can just return this thing. No need to multiply it by 100, we just return. So if we get here to the column-wise processing at all, that means that we don't have a vertical line, which means that we have a horizontal line, which means that this is always true, that we can just return H result. So try to find the vertical. If you don't find the vertical, if you find the vertical, you're done. Otherwise, try to find the horizontal. When you find the horizontal, you're done. We can have even more optimization because we can say something like if is 1, just return it. If at any time we get to a point when we only have one horizontal line, we can return it. We don't need to worry about anything else because we know that if it doesn't have a vertical line, it has to have a horizontal one. But when we're doing the vertical lines, we can have 1 or 0 vertical lines. So we need to take care of that. This is not actually needed, but let's keep it here. The result before this optimization, let's call it, was this 3,520. Let's see if it stays the same. I really hope it does, and I hope even more that this is the correct value. It stayed the same, and it might even be the correct value. Let's see. So we are guessing that our answer is this, and that's the right answer. Great. But before we go to part 2, I just want to emphasize one thing, that we only have 1 star on task 12 because I didn't manage to solve the second part yet. I do have some ideas how to optimize it, how to do it, but that video is not done. Anyway, 13 part 2. First time I see this. Smack, ran into a mirror. Yeah, that's embarrassing. Every mirror has exactly one smudge. You'll need to locate and fix the smudge that causes a different reflection line to be valid. Line won't necessarily continue being valid after the smudge is fixed. Oh, so we need to check. Oh, this is gonna be hard. Mm-hmm. You use the new diffraction line. I don't really get this. Oh, yeah. Both are horizontal lines now. Hmm. This is kind of scary. because we need to change one. So this thing actually ran relatively fast. So for part 2, I will do something that's kind of brute force. The inputs don't look too large. So they are right about in the 100-ish points built, or maybe 200. It says that one of these is an error. And exactly one of these is an error. Exactly one of the items should be of the opposite types. So that means that for this floor matrix, we can generate this many, not that many, but this many floor matrix dot length times. This is the number of fields that we have, and we can generate this many different matrices that have a single character removed. A single character changed. So we're gonna need, this is gonna return a floor matrix array where we will have that many floor matrices. And I will add yet another simple method that says copy matrix. Yep. So this does a double map. Actually, we can use slice here. It will be a little bit more efficient. So this returns the exact same matrix. And I can say width. Number. I said number and then I wrote matrix. So this is the copy. And on this copy, X or Y, we're gonna do this thing. We're gonna change a single element. And then return it. So we're gonna need to have floors, which is an array, and then we just say this. We run through all the x's and all the y's, and for each x and y combination, we generate a new matrix with that element changed, and we just push it. And we can say const unsmudged floor of that, and let's return -1, but here we can console log floors.length and actually return floors.length. Because in the first case, we needed to process 100 matrices, and we did that in about 4 milliseconds. In the second think we will need to process definitely not 63 matrices. Oh, it might be 63. 126 matrices from R2. But I definitely want to see that value for the huge input as well. So how many matrices do we need to process now instead of 100? So from 2 we went to 126 and from 100 we went to 15,000. But note that this code actually generates all those matrices already and seems to be relatively fast. Moreover, if we undo this, this should be 50-ish milliseconds, I would say. Yeah. So we're able to actually generate all those unsmudged floors. Now, it seems that I need to undo the optimization that I did. So, yeah, this is valid. If we have a single vertical mirroring point, return it. That makes sense. But this doesn't work anymore. Because there will be a lot of cases when we don't have a mirroring point. And this doesn't check. This basically gets, if we get to a point when we have one horizontal line that looks okay, we don't need to check it till the end. But here we will have lots of cases when we just don't have a mirroring point. Basically, out of all of those 63 matrices that we generated, only one will have, 62 won't have any mirroring points, one will have. So the result will most likely be 0. And we need to handle that. Since this will be nothing and this will be nothing. And we will actually need to add this part here. I think that we didn't break part 1, 33520, or actually 405. Yep. So now for the smudge mirror number, we need to do that. And for floors dot map, for each floor, get the mirror number. And let's see what we have for these two. This is a problem. We have 400, 400, 100. What was the original thing? We need to change it a bit. Aha. In each pattern, you'll need to locate and fix the smudge that causes a different reflection line to be valid. So we need to do some more work. We need to find whether we have a different line as well. So the first thing works, the mirror number, but I will implement it again, because otherwise we will have to have a lot of small changes, because I want to do another small change so that this thing doesn't actually return a number, a single number, but returns an array. So this will be another method that I will call get all mirror numbers. Because now it says we might have multiple mirror numbers. We might have one line that is a mirroring and yet another line that is mirroring. So we will do the full shebang. We are calculating all the V mirroring points. There might be more than one. We are calculating all the mirroring points. There might be more than one. And the result that we're gonna return is actually this, an array. And we will give all V mirroring points and as well all H mirroring points by mapped up to 100. Let's see what happens now when instead of get mirror number, we are calling this get all mirror number. So note that instead of getting a number, we will get an array. So here we have it. We have 5300, 55555, and once more 5300. So if we remove all the empty arrays, and we can say here filter is not equal to 0. We don't really care which of the lines there are, which element we did, but what we care is about is this. There are actually two elements that we can, most likely the one that is actually the mirrored one, that we can change in some way so that it gives us a different line as well. So it gives us a different reflection line. So if we have the different reflection line, that means we can actually get original line that will be the get mirror number of the floor matrix. So we're getting the original line, and then we will also map once more here like this. So we're gonna remove the original line from the map and filter once again. And if I'm correct, now we will get something very different. Yeah, this is what we need. So we are getting the 300 for the first one and 100 for the second one. And since we're here, I will just say, no, we filtered everything out. And then we can just flat map mirror to reduce one set of line, one level of arrays. So this should have two elements that are 300 and this should have two elements that are 100. And then I will just take the first one because there should be one different line. Otherwise, somebody messed up the input. Actually, let's check that. So we can say from the mirrors, that's a, do we have distinct? Do we have unique? No, I don't have that methods, but because I don't use them too often, but we can always see this. We are creating a new set, we're getting that, and if different lines length is not equal to 1, yeah, let's see if we get this. Otherwise, we just need to... Oh, no, 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 no. Yeah, this is for a single floor matrix. Otherwise, we just need to return different lines of 1. Of, yeah, the first value, because we already know that we only have one value. Everything else looks okay. We are mapping, we are summing. Let's run it on the small input. The small input, we verified that it works, so we're gonna get 400. But what happens with the huge one? The one thing that I really don't want to see, because that means that we got an assumption wrong, is Houston, we have a problem. And we didn't see that. And we got a number which I hope it's correct. Let's see if we got our reflection lines correct. That's the right answer. So this is a bit of brute force solution. There could be a way in actually to analyze the map and see in which direction it almost reflects. But we're just generating, we don't know which one it is. We're going to change all of them and then process all of them, and sometimes this is good enough. If it's not, it just provides us with a baseline. So this actually executed in 300 milliseconds. If this took 5 minutes and was still correct, we would have a baseline that we can build on. Anyway, we are done with task number 13. I will most likely leave task number 12 for the weekend because I have several ideas of how to do it, and I'm not sure which one of them will be fast, which one of them will be slow, which will be optimal, which will be impossible, and we will need to do some experimentation and kind of creative debugging. Anyway, keep developing and see you soon.